For example number 4, we have a sloped roof. And the question is asking us to do the load tracing for this system that we have shown in this slide, knowing that the roofing weight is 5 psf, roof sheeting 3 psf, and then rafters supporting roofing and roof sheeting 4 pound per foot. Pay attention that these loads are along rafter. So you see here that we have a sloped roof. When we talk about along rafter, or so this is along rafter or along a slope, then it's like this. So roofing, roof sheeting, and rafters. The load along the rafter on the slope is provided to us. The live load that we have in this example is a snow load, which is provided on horizontal plane. So when we are talking about horizontal, it's a snow load always provided on horizontal projection. So we have along a slope or along rafter, and then some of the forces or loads that we have are on the horizontal projection. So pay attention that snow loads are normally given as a load on horizontal projection of a roof. And finally, so we have these rafters, roofing, roof sheeting, supported with rafters. These are our rafters, and here you can see the dashed lines. These are our rafters at 24 inch on center. And then on one side, so we have these rafters. We have a beam supporting rafters, and then columns supporting beam. And on the other side, we have a bearing wall supporting rafters. So on one side, rafters are sitting on a bearing wall. That's our bearing wall. And on the other side, rafters are sitting on beam and columns. So before we move to the next step with the load tracing of this structure, let's review projected loads. Consider the case of a snow load on two buildings, one with a flat roof and one with a sloped roof. So we have a flat roof and a sloped roof. If both buildings have the same footprint, then they should both have the same total weight of snow applied to them. This is because the snow doesn't care what the shape of a building is as it falls. But if we don't use it on the horizontal projection, so this is an example of horizontal projection. And you can see the load is 1,000 pound per foot, sorry, 100 pound per foot. And then for 10 feet, the reactions are 100 times 10 divided by 2, 500. But if we assume the load is along a slope and then do the calculation for reaction, same load, 100 pound, 100 pound on a flat surface, 100 pound along a slope. Then the reactions are 707 pounds because this length is larger than 10 feet. You can actually calculate the length. So it's a square root of 10 to the power of 2 plus 10 to the power. But the point is, the weight of a snow should be the same on a flat surface and on a slope surface. So that's why the snow load is normally provided in horizontal projection. So for your class, for the examples that we will go over, for examples, when you see a snow load, assume that it's under horizontal projection. I also wanted to review this concept that for right angle, if we say this is C, base is B, and height is A, then C is equal to a square root of A to the power of 2 plus B to the power of 2. So for example, if we have a triangle where this is 5 and this is 12, C is equal 5 to the power plus 5 to the power of 2 plus 12 to the power of 2, and this gives us 30. Okay, so the next thing that we need to go over is a slope adjustment factor. So the loads are provided along the rafter or along the slope, and we need to convert them from along the rafter to the horizontal projection. So we have 100 PLF. We need to calculate the equivalent load on the horizontal projection. We need to use a slope adjustment factor. A slope adjustment factor is equal to length along the slope, this is along the slope, C, divided by length in the horizontal direction, or B. And then load on the horizontal projection is equal to load along the slope times a slope adjustment factor. So, for example, we have a sloped roof. Roof pitch is 5 to 12. So when we say roof pitch is 5 to 12, it means that height is 5 and base is 12. 5 to 12. And then the load that we have along the rafter or along the slope is 100 PLF. Load on the horizontal projection is equal to load along the slope member times a slope adjustment factor. So in this example, a slope adjustment factor is equal to C, which is 13, divided by B, which is what? So it's equal to 13 divided by, and then load on the horizontal projection is equal to load along the slope or rafter on the slope adjustment factor. So 100 times 13 divided by 4. Now back to the example. So we start with the first member. We start from the roofing system that we have, and we look at rafters. So we start with rafter analysis. The question told us that the roofing is 5 pounds per square foot and sheeting is 3 pounds per square foot, which gives us a total of 8 pounds per square foot. That is the area load. So the area load that we have is 8 PSF. We want to see how much is transferred to each individual rafter. If you remember from the first slide of this example, rafters are placed at 24 inches on center. 24 inch is equal to 2 feet. So if you look at one individual rafter, the spacing between these rafters on center is 24 inches or 2 feet. And each rafter has 2 adjacent members. So half of the distance on the right side and half of the distance on the left side is 1 feet plus 1 feet gives us a tributary width of 2 feet. So for each individual rafter, we have a tributary width of load of 2 feet. Then we multiply area load by tributary width, and we have 16 PLF on a rafter. Then we need to add dead load of rafter. So the total load on a rafter along the slope, so this is our rafter, and the total load on a rafter along the slope is 20 PLF. We need to adjust this load from the along the slope to horizontal projection, And the roof pitch was 5 to 12. So we have A is equal to 5, B is equal to 12, and C is equal to 13. So we multiply 20 PLF, which is along the rafter, by the adjustment factor, which is 13 divided by 12, and then we get 21.7. And that's the load on a single rafter on the horizontal projection. Now we need to look at the snow load. A snow load is 40 psf. Tributary width of a single rafter is 2 feet, so the load transferred, the live load or snow load transferred from the roof to each individual rafter is 80 PLF. So dead load, we have 21.7 PLF. A snow load, we have 80 PLF. The total load on a single rafter is 101.7 PLF. So we have a rafter, and we just calculated the load on the rafter as 101.7 PLF. The rafter on one side is sitting on a beam and the other side sitting on a bearing wall. This is a symmetric system. We can calculate the reactions as load 101.7 times total length, which is 2 plus 12 plus 2 divided by 2. And this gives us 813.6 pounds. So on one side, this is the load transferred to the wall. The other side, the load is transferred to the beam. Now we want to look at the beam. Each individual rafter, so rafters transfer 813.6 pounds at 24 inches from each other to beam. Again, remember that the spacing between the rafters is 2 feet, 24 inches or 2 feet. So every 2 feet, 813.6 pounds is transferred. In order to make the calculations easier, we divide this number by 2 and a spacing by 2. So instead of saying that we have 813 pounds per 2 feet from each other, we say that we have half of that per foot from each other. So 813.6 divided by 2 gives us, this is equivalent to 406.8 pounds at 1 foot from each other, which is PLF. Then we also need to add dead load of beam to it, and we have the total load on our beam as 422.8 pounds per foot. And the reactions are 422.8 times 24 feet, which is the span length divided by. So this is 406.8 plus the load of beam, per foot. We will have 422.8 PLF. That's a symmetric system. Reactions are equal to each other. So we can say reactions are load times 24. And 24 is also, we had it in the previous slide. This is 24. This is 24. And these are the loads transferred to the columns supporting the beam. So again, for each column, we will have 5,074 pounds. Okay, on the other side, so we said that one side rafters are supported by the beam, but on the other side, rafters are sitting um, on a bearing wall. So on the bearing wall, again, same as previous slide, we have these rafters. On one side, they're supported by a beam, on the other side, by the bearing wall. So these are rafters on the wall, and we said that the load from rafters is 817 pounds at 2 feet from each other, which is equivalent to 46.8 at 1 foot from each other, or we can say it is PLF. So on the wall, bearing wall, we also have 46.8 PLF. Now we want to look at each individual stud and see how much load is transferred to each stud. Wood studs are placed at 16 inches on center. So if we want to look at tributary width of a stud, we can say that it has two adjacent members. On each side, there is another stud, and half of the distance on the left side is 8 inches. Half of the distance on the right side is another 8 inch. So tributary width for studs in the wall or tributary wall length per stud is 16 inches or 1.33 feet. So then if we multiply this number by the load that we have on the wall, we can actually calculate how much load is transferred to each individual stud. So you can see here that the load transferred to each individual stud is 541 pounds, but the load transferred to each column supporting the beam is 5,074 pounds. And that is what we expect when we have two beams two columns supporting the beam, the load transfer to the columns is much higher compared to a wall system where we have multiple studs supporting the load transfer to the bearing